Hello everyone, I'm Dawei Liao from Shanghai Jiaotong University. Today I want to briefly present my manuscript, A Unified Distributed Secondary Controller Using a Dynamic Consensus Algorithm in DC Microgrids. The authors of this paper include Fei Gao and Xin Liu from Shanghai Jiaotong University. The presentation will contain 5 parts. First, I'll show you the layout of a DC microgrid and introduce primary control and then the objective of the secondary control. Then in the second part, I'll present the proposed unified cooperative secondary controller. The stability of the system is analyzed in part 3. Simulation results are shown in part 4 to verify the proposed control method. Finally, I'll give you the conclusion of the manuscript. In the right side of this page shows the configuration of a DC microgrid. Multiple DGs are connected to the same DC bus through LC filters and feeder lines. Each DG is equipped with a hierarchical controller, which contains 2 parts: group-based primary control and cooperative secondary controller. Group control is expressed in this equation, where a virtual resistance RD is applied to regulate the voltage reference using the inductor current. With group control applied, current sharing can be achieved without communication. However, with only group control adopted, the voltage will deviate from the nominal value, and the current sharing performance is affected by feeder line resistance. In order to solve the 2 problems, the droop curve is shifted by a correction term, delta V, which is generated by a secondary controller. The 2 objectives of the secondary control are average voltage regulation and accurate current sharing. Most of the secondary control strategies nowadays achieve the 2 objectives by 2 separate correction terms and 2 according parallel controllers, as shown in the right side of this page. But this kind of parallel secondary controller has 2 drawbacks. First, since the 2 parallel controllers will affect the same output variable, delta V, they will affect each other's performance. Therefore, it is difficult to design the control parameters to get a desirable dynamic response. Secondly, the 2 controllers require 2 communication variables according to the control objectives. Thus, it will increase the communication burden. In this manuscript, a unified secondary controller is proposed. The simplified control structure contains only 1 integrator, simplifying the control's design, and requires only 1 communication variable, thus reducing the communication burden. The proposed controller adopts the dynamic consensus algorithm to estimate the global average of zeta, which will be introduced later. The step size of the consensus algorithm is designed following this rule to guarantee the fastest convergence, where L is the Laplacian matrix. In the proposed controller, a state factor is introduced, which is defined as the ratio of the output voltage and the normalized current. And the input of the secondary integrator is the difference between the nominal voltage V star and the product of the normalized current and the estimated average of zeta. To better understand how the controller works, here is the steady-state analysis of the controller. First, at the steady state, if the consensus algorithm is implemented properly, each controller can accurately estimate the global average state factor at the steady state. Thus, for each controller, zeta average is equal to the average of all zeta. Then, if the control parameters are properly designed, the input of the secondary integrator should reach 0 at the steady state, which means that the normalized currents reach convergence. So, accurate current sharing is achieved. When the normalized currents reach convergence and the integrator reaches steady state, the average of zeta is equal to V star over the normalized current. The normalized current here can be eliminated, so the average voltage is restored to the nominal value. In part 3, the system stability is analyzed. There are 2 points worth mentioning in the established state space model. First, the dynamics of the consensus algorithm is neglected, which means that the zeta average of each controller is assumed to be the exact average of all zeta. Second, since there is a product of variables in the input, the controller is linearized around an equilibrium point. Here are some eigenvalue contours of the system. We can see that a larger secondary integral gain, a larger droop gain, or a larger load current could degrade the system's stability. In Part 4, simulation results are shown. In Case A, the proposed secondary controller is activated at 0.5 seconds. The resistive load changes from 10 ohms to 5 ohms at 1.5 seconds, and the current load changes from 5 amps to 1 amp at 2.5 seconds. We can see that regardless of the load change, the average voltage is well regulated, and the current sharing is achieved within 0.05 seconds. In Case B, the secondary control is activated at 0.2 seconds, and the resistive load changes from 10 ohms to 5 ohms at 0.8 seconds. The system for performance under different values of KISV is shown in Figure 7 and Figure 8, compared with cases where KISV equals to 10. When KISV equals to 30, the average voltage has a faster dynamic response, while it takes more time for currents to reach a consensus. Thus, there is a trade-off between the dynamics of the two objectives. In Case C, the resilience of the proposed secondary control scheme to communication link failure is tested. The secondary control is activated at 0.2 seconds, and the resistive load changes from 10 ohms to 5 ohms at 0.8 seconds. The communication link between converter 1 and 2 breaks down at 0.4 seconds and recovered at 0.9 seconds. We can see that regardless of the communication link failure, the average voltage is regulated and the current sharing is achieved. Finally, we come to the conclusion of the manuscript. First, the proposed strategy, containing only one integrator and one communication variable, is proved to achieve accurate current sharing and average voltage restoration with a dynamic consensus algorithm, even under load changes and communication link failure. Second, eigenvalue analysis shows that a larger secondary integral gain, a larger droop gain, or a larger load current could degrade the system's stability. However, the system still remains stable at a wide range of parameter variations. Third, in terms of the dynamics, a larger secondary integral gain accelerates the voltage restoration while influencing the current sharing dynamics. That's all for my presentation. Thank you for listening.